Hello everyone. Welcome to today's webinar hosted by BIS Research, which is a leading market intelligence firm dedicated to providing insights into emerging technologies and their impact across various industries. We are thrilled to have Faisal Ahmad, CEO of BIS Research, as our expert speaker. Welcome, Faisal.
Thank you, Jaya.
So, today's webinar will delve into the innovative role of quantum computing in revolutionizing hydrogen production, which is a crucial element for sustainable energy solutions. When we talk about integrating quantum computing with hydrogen, what's the first thought that comes to your mind?
Thank you very much for having me to discuss such a very interesting topic. It's always like crystal ball gazing into future. And so talking about, let's say, quantum computing and hydrogen. So we can basically, the way I look at quantum computing is like, we all know how classical computer work. It's like almost a part of our daily routine now. So when you have to think about classical computer, it is like a super efficient librarian who has to actually check each book. Let's say you go and request a book in the library, and the classical computer is like is a super efficient librarian who will actually go to each shelf and check all the book one by one, is printing from shelf to shelf, but he can only look at one book at a time. But if you have to draw parallel with quantum computer, you can basically think of it as a wizard librarian who can basically clone himself to multiple librarians. So basically, you go and make a request to this wizard librarian. Instantly, he will clone himself to as many librarian as needed, and those all of those librarian would likely be looking at each bookshelf at one time. So basically, it's like in the blink of an eye, the copies reunite and hand you the book you were looking for. So it's certainly like magic. That's the difference between classical computing and quantum computing. And certainly, if we talk about quantum computing in today's in realm of hydrogen production, so it certainly has a lot of potential to solve complex optimization problem more efficiently than a classical computer. If you look at hydrogen production, one of the key issues within hydrogen production is that of finding the right material, right catalyst. And quantum computing can basically help accelerate the discovery and development of new material with superior properties for energy storage, such as more efficient batteries and superconductor. So with the combination of quantum computer and hydrogen production, you can basically look at a very, very green future and energy efficient future.
Yeah, that was a great introduction to the topic. When I think about quantum computing in the production of hydrogen, the first thing that slides in my mind is what is the chemical process? How quantum computing can help simulate the chemical processes for making hydrogen?
That's a very interesting question because unless it's very simple, right? Like you break water, you basically, when we look into hydrogen as a source of energy, it's of course so abundant that you can simply think of breaking water into hydrogen and oxygen through electrolysis process. And what quantum computing does is quantum computing can significantly enhance the simulation of chemical properties by providing more accurate and efficient modeling of molecular and reaction dynamic. For example, let's say quantum computers can model the behavior of electrons and atomic interaction with high precision. Now, what does this capability do? It allows precise calculation of electronic structure, accurately calculating the electronic properties of molecule involved in hydrogen production, such as catalyst and intermediates in the reactions. Similarly, it also gives you a very fast, accelerated time for simulation of complex reaction. Basically, the way I always think about quantum computing and its application in hydrogen production is like you can basically imagine a world where scientists are trying to create the perfect recipe for a clean and limitless energy. Now, when I'm saying why a recipe, that you can basically draw parallel with scientists as master chef who are trying to create a perfect loaf of bread, and they know that the yeast or the catalyst is crucial for the bread to rise and fluff. However, finding the perfect yeast is a complicated task, and quantum computing acts like a super precise microscope that can exactly see how the yeast molecules are interacting with the flour and water. Now, this super microscope helps the scientist, or the master chef in our case, design the best possible yeast, making the bread rise perfectly every time. So when we are looking for catalyst in terms of hydrogen production, so this is exactly what quantum computing does as a super microscope. Similarly, it is actually a very useful tool in terms of intervening in the reaction pathways. For example, you can see, look at again the same example of master chef baking. Now there are various steps in basically creating a very fluffy bread. It is mixing, kneading, and then of course baking. Now each step requires precise timing and condition, and chefs are trained to do that. With quantum computing also, our master bakers can create a magical map of the entire process, showing the exact temperature and time needed for each step to achieve the perfect loaf, and he can basically intervene at the right time. So what it does effectively is that it helps create large scale simulation in a in a fraction of time, and then also enable scientists and chemists and physicists to do real time adjustment. So effectively, with what you can see, quantum computing coming to aid chemical process in a very, very big way, and leading to a cleaner and more sustainable energy future for us.
That was a quite fascinating insight. If I talk about the hardware aspect, do you think that any special hardware requirement is there in the production of hydrogen if we are using quantum computing to integrate that?
Interesting. I think fundamentally we need to understand essentially that the hardware components required for quantum computing in hydrogen productions are generally not exclusive. It is more or less the same set of hardware that are needed, right? They're fundamental to any application or field within quantum computing. So whether it is quantum bits or dilution refrigerators or quantum control electronics, these are all the same building and foundational block. But the real difference arises in terms of software and algorithm. For example, quantum software and an algorithm like variation quantum eigensolver, which is called VQU, is a quantum algorithm for quantum chemistry and simulation, and are developed to solve a variety of quantum problem across different fields, especially within chemistry, observing reaction within chemistry and molecular intervention. So in terms of hydrogen production, specific algorithms for quantum chemistry simulations are applied to optimize hydrogen production processes and discover new materials. So it is largely the software and algorithm which is differentiated, kind of unique to the hydrogen process, but not the hardware.
So it's quite clear that the hardware requirements are not that specialized.
Indeed.
Moving on, let us discuss what are the key research focus areas that we effectively need to integrate quantum computing in the production of hydrogen.
Bob, I think you rightly pointed out to the fact that both these technology, especially quantum computing and its application in hydrogen production, which in itself is a new trend and a very promising one, though, are in nascent stage. And a lot of research is happening around these things. So combining quantum computing with hydrogen production involves several key research activities aimed at optimizing and innovating various aspects of hydrogen production, such as catalyst design and optimization, A. B, reaction pathways and mechanism. I have just talked about it in my introduction. Likewise, molecular dynamics. And finally, material discovery. So for example, material discovery not only for production, but also for storage. It is not a matter of just producing hydrogen, but the complex issue, a real issue is in terms of storing hydrogen also. So by using quantum computing, we can predict the properties and behaviors of new material, such as metal organic frameworks and complex hydrides, which could be used for efficient hydrogen storage and production. Likewise, if you look at photocatalytic and photoelectrochemical processes, quantum computing can model light absorption, charge separation, and transfer process in photocatalysts, leading to the design of more efficient systems for converting solar energy into hydrogen. So scientists are likely so if you can basically think of it like this, that scientists today are with the tools like quantum computing, scientists are like modern day alchemists. They're striving to transform base material into powerful catalysts for hydrogen production. They encounter, let's imagine they encounter a problem, which is like existing catalysts are inefficient and costly. So how do they solve it? They basically take the quantum model, the quantum processors, and simulate the behaviors of electrons and atoms with incredible precision. And with quantum computers, the scientists and their team begin to design and optimize new catalysts, visualizing how atoms interact at a never seen level before. Now, this breakthrough basically accelerate the production by finding the right catalyst without actually getting into production. So which is basically synthesizing that simulation and in fraction of time. Areas wherein the key research activities are happening is like in unveiling reaction pathways. Like today, chemists are puzzled by the complexity of the chemical reaction involved in splitting water. There is electrolysis, which is general. All of us know that okay, you can use electrolysis to split water into hydrogen and oxygen. And but traditional models are too simplistic to capture the intricacies within these reactions. What happens with quantum computing? It can, as I mentioned earlier, also that it can create a map of the entire reaction pathways, identifying the energy peaks and the valleys that molecule traverse during the reaction. And that becomes a very important investigation for different institution at the current setup. Similarly, understanding the molecular reaction and dynamics is very important. So effectively, if you think of it like today, in today's scenarios, a pragmatic engineer faces the challenge of bringing these quantum power discoveries from the lab to real world. Now, one can basically develop hybrid systems that combine classical and quantum computing. The classical computer basically handles the large scale data processing, while the quantum computer performs the intricate simulation and optimization. And these research are happening across the world.
So, research and development is definitely playing a key role in the advancement of this field. But if we talk about this real world application or some case studies, do you know any current research project, or could you introduce it with any case studies that has
Sure.
been already there where quantum computing has been improving the production of hydrogen?
Yeah, very interesting. I think that's exactly where we have to go when we are trying to understand such a complex and early stage technology. We have to look at what are the different lab use cases and applications that are being developed. So just to give you a sense of it, there's a lot of activity that is happening, especially for active hydrogen production and using quantum computing. So there is a few names I can basically recall top of my mind are IBM's quantum catalysis initiative. So it's basically focused on finding the right catalyst for hydrogen production. That's one example. Again, IBM quantum simulations are identifying materials with low energy barrier. So it's basically looking at the materials with has low energy barrier, so that the reaction can happen at a much lower energy with much lower energy input. That is basically making the system and the process much more efficient. And likewise, you have ongoing project at Google, which is Google AI Quantum Chemistry. It is especially looking at the chemical reaction involved in hydrogen production. And Google has patented its own advanced quantum algorithm, much similar to variation quantum eigensolver. And with this, they have been able to show some promising result. And the project focus remains on identifying the most efficient reaction pathway, minimizing the energy losses and understanding transition state. So majority of projects today are designed at molecular level intervention in terms of reducing energy input in terms of generating hydrogen using as a feedstock for energy production. There is an interesting case study or example from Zenatu, a quantum computing startup, which is basically using photonic quantum computers to predict the properties of new materials for hydrogen storage. One part is production, and as I mentioned, IBM and Google have some really promising initiative in the industry side. And then there is a startup basically looking at the energy storage, hydrogen storage, this thing. So their material discovery platform, the Xanadu material discovery platform, basically leverages quantum simulation to explore novel compounds like metal organic frameworks and complex hydrides. On the university side, which is it's also very promising, and the journey of a technology, as you would know, Jaya, it goes from a university lab to commercial labs. But in case of hydrogen energy and especially quantum's application in energy, it is actually happening parallelly. There is university intervention. There is, of course, corporate intervention happening very parallelly. So looking very promising to me that in the next 5, 10 years, we'll see major breakthrough. And some university project that I can recall, top of my mind, are your Harvard University's quantum photocatalysis research. It is a very interesting research wherein researchers at Harvard universities are using quantum computers to improve photocatalyst materials that are basically use sunlight to produce hydrogen, right? Now, this project basically involves simulating light absorption and change transfer process in various photocatalytic materials. By understanding these processes at a quantum level, the team aims to design more efficient photocatalysts that can convert solar energy into hydrogen more effectively. So basically, paving the way for sustainable solar to hydrogen production, right? Instead of instead of current method of electrolysis. So this could be very, very innovative as we and could be a groundbreaking thing in the future.
Yeah, it's innovative and it's inspiring to see that the practical implementations are already taking shape. So, if we consider the economic implications, so what economic impacts do you foresee for the hydrogen market?
Well, the it is very again, I will have to wear my analyst hat in terms of analyzing the economic impact of hydrogen, and but I will do it with a caveat that I'm not just talking about hydrogen production, but I'm also talking about using quantum computing for hydrogen production, because the key issue within hydrogen production remains that of energy efficiency, and which basically transcends into net concerns of net zero emissions and basically sustainable goals of energy generation. So that's a major issue right there, right? And but what we are foreseeing that if there is a quantum intervention and the model and the examples that we talked about, they are successful, and they while they are, and some of them are showing very positive result, it may lead to 30 to 40% reduction in production cost for hydrogen, which means totally democratizing the access of hydrogen to various end user. Also basically increasing, making it super competitive with fuels like fossil fuels or any other renewable source of energy. So one of the major economic impact would be that of finding, various applications for expansion of hydrogen usage, like cheaper hydrogen could boost the adoption of hydrogen fuel cell. While we are hearing a lot about electric vehicle today with lithium ion battery, with the chemistry's innovation, but if you have hydrogen at a 30-40% reduction from the current process, you will see a massive adoption of hydrogen fuel cell, which is more sustainable than basically disposing a battery today, whether it is solid state battery or lithium ion battery. Also, it's situation, the issue, especially with electric vehicles, you see that today, when there's an issue in terms of ignition temperature, the issue with solid state battery or lithium ion battery is that it is very difficult to achieve that ignition temperature in electric vehicle today, these fuel cells or this battery system. But with hydrogen, this is not an issue. So industries, not only fuel cells adoption for hydrogen at at the vehicle level would happen, but also industries that require high temperature processes or use hydrogen as a feedstock, like a steel manufacturing, chemical production, would certainly benefit massively from lower cost, leading to greater uptake and innovation in these areas. And finally, providing critical energy in access, continuous energy access at remote location becomes much easier when you have solved not only production issue but hydrogen storage issue. By using quantum computing, you can basically balance it out energy supply in remote areas with using hydrogen and other renewable sources as well, right? So in addition to its real world benefits, it's also very obvious that with hydrogen, which is abundant in the universe, right? You see water is so abundant that if you are able to probably process hydrogen through water, you are able to probably create altogether a new avenues of growth for the world. And the environmental impacts are real, plus it's very good for the environment. The geopolitical and the governmental, basically talking about the ESG spectrum, the geopolitical and the governmental intervention impact would also be very, very encouraging. For example, you'll see massive job generations into new industries. So if we see 30-40% reduction in hydrogen production cost, it will have transformative impact on the global economy. Overall, the economic landscape for hydrogen would become more robust and dynamic, and basically paving a very promising future for us in terms of energy sustainability.
So the economic impact could indeed be transformative, but we still have to consider this that quantum computing as a technology to increase the efficiency of hydrogen production, it's quite at the nascent stage. So there, of course, exist some major challenges. It could be technological or infrastructural. What are those major challenges that you think that exist to integrate quantum computing with the production of hydrogen?
Right. So with any, as you rightly pointed out, that it's a nascent technology, and with every technology, there are issues, right? There are concerns. Like you can, like, let's before we talk about quantum computing issues within quantum computing ecosystem, let's understand that within hydrogen also the major issue is the energy input, right? You don't want to
Yes.
probably create a greener fuel by actually investing more energy. So that's a wrong approach. Similarly, if you look at like quantum computing, right? There are a few very fundamental issues that still need to be solved to for commercial application. One of them in terms of hydrogen production could be when we talk of complexity of chemical reaction. Simulating chemical reaction involved in hydrogen production, basically, such as water splitting, it involves quantum mechanics, right? And accurately modeling these reactions require significant computational power and precise algorithm. So there are two issues. One is like, how do you reduce computational power, right? And how do you basically enhance your algorithms? While these are issues, there are promising solutions that are being worked upon. Like, for example, developing advanced quantum algorithm tailored for quantum chemistry, such as VKU. As I mentioned, Google is working on the same.
Hmm.
Likewise, if you look at catalyst design, right? Now, this is again a problem that so I'm talking about the technical problem. One is complexity of chemical reaction. Another one is catalyst design. Now, catalyst design for hydrogen production processes like electrolysis or photocatalysis, right, is highly complex. These catalysts must be optimized at the atomic level to enhance reaction. Now, again, there are quantum hardware to handle large scale and high fidelity simulations. And that has shown promising result. Almost 90-95% result is achieved already. So I believe it's again a matter of time that this issue will also be solved. Finally, and the most important issue, which we must understand, that we live in a world which is basically, what do you say, like, which is basically dominated by classical computers today, right? And so how do we integrate classical computing or classical methods with quantum computing? Now, that's a major problem, right? Integrating quantum computing will certainly be needed to accelerate, the adoption and increase the computational capacity of existing models, right? So the solution lies in creating seamless hybrid, basically creating a hybrid computing framework that combines quantum and classical computation, ensuring compatibility and effective data exchange between the two systems. And I think there are a few research activities happening at IBMs and a few startups that are talking about solving this issue. So that is also looking very promising. And finally, that the one issue that comes to my mind is a common issue which happens with any deep technology or emerging technology. That there is, of course, a need for a specialized technical expertise, right, to develop and apply quantum computing, which is, of course, very limited right now. So that would remain a major issue. The government and the academicians would have to look into solving this issue as we move along.
Yeah, so the integration of quantum computing for the hydrogen production, I think these challenges need to be in focus, and we have to find a successful solution to it. And since you mentioned startups, I would like to ask you that what is the investment landscape, especially for the startups? Do you think that there is any opportunity for collaboration between the startups and the big companies, or what are the investment opportunities that you think could emerge by the integration of quantum computing as a technology in the production
Yeah.
of hydrogen in next 5 to 10 years?
Interestingly, like with quantum computing as a core science discipline, there have been significant investment done by governments and corporates alike. But in the next 5 to 10 years, I believe there are the opportunities for startups is going to be immense, right? And likewise, there would be immense opportunity for collaboration between researchers and companies that are producing any end use, be it hydrogen or any drug discovery. So for computational excellence, right, quantum computing is a brilliant tool, right? And but if we come back to, like, of course, in terms of opportunities, it looks very promising. I don't have numbers on top of my mind, but I think it would be certainly a multi-billion-dollar opportunity for startups to look into, to work and solve these really complex problems. And but immediate opportunity that I can think of that companies or a startup should focus on is one is in terms of creating technologies for producing green hydrogen using renewable energy sources
Yeah.
such as solar and wind to power electrolysis. Basically, to power electrolysis, you have to create technologies, and that is an opportunity area that a startup should be looking at. And that would be something a lot of there's a government grant available for some of these power electrolysis processes, as well as corporates are and VCs, communities, and private equities are pumping in and looking at right candidate to invest in. Likewise, another opportunity area that I feel could be of great interest for startups in the coming days would be fuel cell technology for application in transportation, stationary power generation, and portable devices as well, right? All the devices that we carry today, we carry, all of us have like 5, 6, 8, 9, 10 devices almost. So that's going to be a big area and big opportunity. And using hydrogen as a source would be super incredible, right? And one additional thing that I'm seeing here, as I talked up earlier in my observation, that hybrid system and integration, right? So the opportunity certainly lies. The third opportunity, I think this would be one of the big opportunities, but a complex one to solve, is in terms of creating hybrid system that I mentioned can combine hydrogen production with other energy system, such as batteries or supercapacitor, for more resilient and efficient energy solution, right? And so how companies can do it is like they can partner with energy companies or utility companies and academic researcher to design and deploy integrated energy systems like this. And this could be a big opportunity to solve. And it can only be solved in a when multiple stakeholders come together. So therefore, I fundamentally believe that for quantum computing to make a significant impact on hydrogen production, we have to look at a very standard playbook of adopting a technology like this by forming consortia between quantum computing firms, hydrogen companies, and academic researchers to explore and implement quantum solutions.
Of course, I think even collaboration will undoubtedly act as a catalyst for this innovation.
Absolutely.
So, as we reflect on the insights shared by you today, it's clear that the future of production of the hydrogen looks quite promising with the integration of quantum computing.
Absolutely. There's no denying to the fact, right? But of course, it's like with any new technology, it has to be proven and worked around in the long term, right? And opportunities are immense for startups and big corporates to solve these issues. And the future looks really promising for adoption of quantum and accelerating hydrogen production for adopt. And we are actually looking at a very green future with this intervention, I would say.
So, as we move forward to the closing of this webinar, I would like to thank Fazil for joining us and sharing key insights on quantum computing as a technology in the production of hydrogen, which is undoubtedly a technology that not only promises to enhance the accuracy and speed of the chemical simulation, but I think it also opens up new pathways for materials and catalyst design, ultimately leading to more effective and environment friendly hydrogen production techniques.
Oh, thank you, Jaya. It has been incredibly interesting conversation, couple of topics very close to my heart, energy efficiency and quantum computing. So I really look forward to more discussion around these interesting marriage of technologies. Uh, Thank you very much.
Thank you everyone for joining us, and we would love to hear from you. Please share your thoughts about anything that you or the any doubts that you are having in the Q&A section below. And if you enjoyed today's webinar, don't forget to follow our channel. Stay updated with the latest insights and stories from the frontier of technology. Thank you so much.